It's time to solve another physics problem. A stone is thrown vertically upward with a speed of 17.3 meters per second from the edge of a cliff, 110 meters high. How much later does it reach the bottom of the cliff? What's the speed just before hitting? And what's the what total distance did it travel? So those are the questions we want to ask. And this problem in particular is very, very important to set up properly, to really visualize the physics, to put that into a simple physics diagram, and to get the signs correct. So let's start with a simple physics diagram. I'm going to go ahead and I'm going to draw my cliff. So this is going to be my cliff. There it is. Add a little shading to it. And this is where the problem's going to start, right there, right at the top of that cliff. And the stone is going to get thrown upwards like this. And then it's going to come all the way back down. And let's go ahead and label some information here. The stone gets thrown up with an initial velocity of 17.3 meters per second. Yep. And we want to figure out how much time does it take to go all the way up and then all the way back down to the ground. So I want to figure out that time. Now I also know some other information. I know the displacement right here. So that equals 110.0 meters. And I also know the acceleration due to gravity, because the problem actually starts as soon as that stone leaves my hand. So as soon as it leaves my hand, it's in midair. And it stays in midair, stays in midair, stays in midair, stays in midair, stays in midair. And then the problem ends just a split second before it actually hits the ground. So that entire up and down motion, the stone is actually in free fall. It's under the influence of gravity. And whenever anything is under the influence of gravity, we're going to put 9.81 meters per second squared. All right. Now, the next thing is we have to define our axes. What's the positive direction? What's the negative direction? So as a general rule, I like to make the initial direction of motion positive, because in most cases, it makes the math a little bit easier, but you don't necessarily have to do that. So the initial direction of motion is up. So I'm going to go ahead and I'm going to make up positive. And by default, that makes down negative. So I'm just going to put a little note here. I'm going to make up positive. That's my positive direction. And then downward would be negative. So let's go back and revisit some of these quantities here and make sure they have the proper sign. So let's start with this. Initially, the stone was thrown upward at 17.3 meters per second. So this velocity, this initial velocity, is in the upward direction. Up is positive. No problem. I'm going to leave it as is. Let's take a look at the acceleration. Now, when you think about the acceleration due to gravity, gravity is always trying to pull things down towards the ground. Even when they're going up, gravity's trying to slow them down and pull them in the opposite direction. So, the way I want you to think about gravity is just ask yourself this question. In which direction does gravity always try to pull any object? Down towards the ground. So, we made up positive, that means down towards the ground is negative. So the acceleration due to gravity is negative, 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 negative. It's everywhere throughout this entire motion, right? It's still going to be negative, 9.81. Now, let's take a look at the displacement. Displacement is also a vector quantity. It's got a direction. This is where we're starting, right here. And you can see the displacement. Remember, the definition for displacement is how far the object is from its initial starting position. So this is where the object ends up. This is where it started. It ends up below its initial starting position, below its initial starting position. So again, I defined up as positive and down as negative. So it's important to get those signs correct, or you're just not going to get the right answer. Now we've done that, literally the hard part is done. That was the hard part right there. Drawing the diagram, writing down the given information, and deciding whether it should be positive or negative. Once you're done with that, it really isn't that hard anymore. So we're looking for the time from here all the way up and all the way down. So that has to be in my equation. And then I also, have this information available to me also. So what I'm going to do is this. I'm going to try this equation right here. Displacement equals the initial velocity times the time plus 1/2 AT squared. So I'm going to go ahead and I'm going to use that equation. Now, I know my displacement. You might be thinking, well, we're trying to find the time from here all the way to here. And the displacement just goes from here to here. That's true, but this equation takes all that into consideration. All right? And one of the ways it does it is because that initial velocity is going to be in the upward direction. So let's just go ahead and plug in the numbers. Negative 110.0 meters. The initial velocity is positive 17.3 meters per second times the time plus 1/2 negative 9.81 meters per second squared times the time squared. Now there's no good way to really simplify this here. We're going to have to use the quadratic equation. So what I want to do is I want to just rearrange this equation in the form of ax squared plus bx plus c equals 0. So what I'm going to do is I'm going to take all this information here and I'm going to bring it over to the other side. So here, I'm going to take 0.5 times that, and it's going to be a negative number. And when I bring that negative number, nt squared, over to the other side, it's going to be positive. And when I do that, I get 4.905. So I'm going to go ahead and write that, 4.905. And for clarity, I'm going to go ahead and omit the units, and I'm going to write t squared. So, got it, ax squared. Then I'm going to bring this over to the other side. And when I do that, I'm going to make that negative, right? Because I want to add negative 7.3 to both sides. So minus 7.3 t. I'm going to leave that where it is. So minus 110.0 meters equals, because I've taken everything from here and brought it to the other side, there's nothing left. So it's going to be 0. So this is my A, this is my B, and this is my C. And when I put that into my calculator, and most calculators can handle quadratics pretty easily, my time turns out to be 6.8168, 6.8168. I'll just leave it there. And then I'll round off, what do we got? We got 3 significant digits, 3, 3. I'll round off to 3 significant digits, 6.82 seconds. So that's going to be our answer. And the reason I left that unrounded off answer there is because this has a part B and a part C. And chances are, we're going to need that information. And we want to use the unrounded off answer in the next 2 parts. All right, so part B. Let's take a look at part B. So part B is, what is the speed just before hitting the ground? And what is its velocity just before hitting the ground? So those are similar questions because it turns out the magnitude is going to be the same for both. However, the direction for the velocity also has a direction. The direction is actually going to be what? The velocity just before it hits the ground is going downward. So I would expect a negative number. But whether it's speed or velocity, at least for this particular problem, the magnitudes are going to work out to be the same. All right, so let's start with the velocity part first. What's the velocity just before hitting? So right here, I want to figure out what's the velocity just before that stone hits the ground. So obviously I want final velocity in my equation, and I'm going to go ahead and choose this equation. Velocity final squared equals velocity initial squared plus 2ax. And there's some other equations you could use also. Remember, you figured out the time here, so you could actually use an equation that has time in it too. All right, so let's take a look at that. I'm looking for the final velocity. Good, check. My initial velocity, positive 17.3 meters per second. And we're going to square it, plus 2. Acceleration is negative 9.81 meters per second squared. And then the displacement from here to here, that's the displacement, negative 110. So there we go. So we want to square that and add it to that, take the square root. So let's go ahead and do that, and I end up with 49.573. 49.573 meters per second. And we'll round off to 3 significant digits again, so 49.6 meters per second. And let's make sense here of this. So whenever I take the square root of a number, it's going to be plus or minus some number. So I have an option. I can choose plus or I can choose the minus. And I'm going to choose the minus because it makes sense in terms of this problem. Remember, I defined up as positive, down as negative. So this stone is in the downward direction just before it hits the ground. So I'm going to make that negative. At least the way I set up the problem, negative is going to make more sense. So that's going to be my final answer for part B. Now, I've also got an interesting little extra to talk about here. So, before we even go on to part C, I'm looking for a red marker. Here it is. Let's take a look at this. The object goes up in the air at 17.3 meters per second. That's the initial velocity. And then it's going to slow down, slow down, slow down, slow down, slow down, stop for a split second. And then it's going to start to speed up, speed up, speed up, speed up, speed up. My question is, how fast is it going right here when it's even with where it went up in the air? So these 2 points are even with each other. How fast is the object going there? It's going in the downward direction right there. But how fast is it going? Well, remember, the same force that's slowing it down on the way up is speeding it up on the way down. So it turns out it's also going to be 17.3 meters per second, right here. However, remember, we're talking about a velocity. It's got a direction. We're now in the downward direction. So I'm going to put a negative because I made up positive and down negative. So let's think about this problem again. Let's think about part B again. I want to find that final velocity. If I just think about it from here to here, look what I can do. I could say, hey, that's my initial velocity right here. That's my acceleration. That's my displacement. And now I can actually find my final velocity. And guess what? I will get the same number. In fact, we could even use the same equation. Initial velocity, instead of being positive 17.3, is going to be negative 17.3. And what do you think I get when I square a negative 17.3? Yeah, the same as when I square a positive 17.3. So that really doesn't change. We're still going to use the same acceleration and the same displacement, so that doesn't change. Notice we get the same answer, just a different way of thinking about that problem. And it's good when you first start physics to try to think about the problem in different ways, kind of confirm your answer. All right, let's go on and do part C. I want to find the total distance. So, well, I want to find the distance. That's the total length traveled. All the way up, all the way down. Now, the good news is I already know this right here. That's 110. The distance would be a positive 110. So I'm thinking to myself, if I can figure out how far it is from here to here, that's the same distance as it would be from what? Here to here. So if I find this number from here to here, I'm going to multiply it by 2, and then I'll add 110 to it. And that's going to be my distance. So again, just kind of break this problem up into pieces here. If I can find the displacement from here to here, again, multiply that by 2, that gives me this entire distance, and then add 110 to it, that's going to be my answer. So let's go ahead and do that. And again, I'm going to use the same equation. Velocity final squared equals velocity initial squared plus 2ax. But now, this is where I'm starting, right here, and this is where I'm ending. So my final velocity is now going to be 0. I'm just taking this into consideration right here. My initial velocity is 17.3. That's how quickly the stone, or that's how fast the stone was launched. Slows down, slows down, slows down, slows down, and for a split second at the very top, it's going to be 0. And that's all I want, because I'm just considering this part of the flight right here. So let's go ahead and do that. So the final velocity is going to be 0. The initial velocity is going to be 17.3 meters per second. I'm going to square that, plus 2. Acceleration due to gravity is still negative 9.81 meters per second squared. And the displacement, remember, that's what I'm actually looking for. How far is it from here to here? So I'm actually looking for that. So when I go ahead and I crunch the numbers, take that, square it, bring it to the other side, that's a negative. And then I take this negative number and divide that into it, and I end up with a positive x. And my positive number should be 15.254. So 15.254 meters. And it should be positive, right? Because this is above my initial starting position, and I defined up as positive. So I should get a positive value for that, and I did. So that is the length of this first part of the flight. And then if I times 2, that'll give me the distance from here and all the way back to here. So if I add another 15.254 meters, this is the up, now we're coming back down, and then I gotta add another 110 to it. So plus 110 meters. When I add that all together and round off to 3 significant digits, I'll get 141. 141 meters. So that is going to be our total distance. And that's it for this problem.